I know I've mentioned it before, but one more time, let's make a distinction between weight and mass, as these are two quantities that are often mixed up in everyday language. Okay, so first and foremost, you have to recognize that weight is a force. It's actually a force of gravity, if you want to be specific. And we can calculate that in one of two ways. If you want to go about it the long way, as you probably saw in the last video lesson, if you consider this drawing that's very ridiculously out of scale, so the m number 1 is the mass of you, and m number 2 is the mass of the Earth which you're standing on. The distance between the center of you and the center of the Earth, for all practical purposes, is the radius of the Earth. So this is a force you can calculate by multiplying your mass and the mass of the Earth together, divide it by the radius of the Earth squared, and then factor in this constant. But a lot of the values in that equation can be pre-calculated. We know the value of this constant, we know the mass of the Earth, and we know the radius of the Earth. So a shortcut says you can find your weight, which is really the force of gravity, by taking your mass and multiplying it by the acceleration due to gravity. And the acceleration due to gravity points in a particular direction, doesn't it? So viewed broadly at a distance from the Earth, the acceleration due to gravity always points straight in toward the center. So if we're fixed at this location, let's say the acceleration due to gravity points straight down. So since it has direction, it's a vector quantity, which means the force is a vector quantity. When you multiply a scalar times a vector, you just get a scaled up vector that points in the same direction. Okay, so weight is a force and weight is a vector. Mass is just the same thing as inertia, and it's really comes down to how much matter makes up any object. It's a scalar quantity. It's measured in kilograms in the metric system. By the way, weight is measured in newtons. So there's a key distinction between the two. They're not measured in the same units. You would never say how many kilograms something weighs, and in the same vein, you would never say how many newtons of mass something has. In the English system, we say pounds for your weight, for force. In the metric system, mass is measured in something called slugs. And that's a unit we don't often reference, although it still lingers in everyday language in some regard. I think if you've ever stepped on the gas pedal of your car and it doesn't accelerate a whole lot. From Newton's second law, we know acceleration should be equal to force divided by mass. So we think of stepping on the gas pedal as applying a force. And if we find from that force we get a very low acceleration, then it must be that the car is behaving as if it has a lot of mass, or in other words, is being sluggish. Okay, so there you have it. Mass is a scalar, force is a vector. Mass is measured in kilograms, force or weight is measured in newtons, and we can calculate the weight of an object if we know the mass just by multiplying by this factor equivalent to the Earth's gravitational field strength, otherwise known as the acceleration due to gravity. So we can say either F equals mg, or we can say capital W equals mg, because weight is a force. Okay, knowing this, how does it help us in some problem solving that you'll encounter in this unit of study? Here's a good example. A grocery bag is full of 5 kilograms of groceries, and it's sitting on the ground maybe after a rainy day in a wet parking lot. You may have had to do this before. Set your groceries on the ground as you open up the trunk of your car, and once the paper bag gets a little bit wet, it's no longer as strong. So the problem goes on, tells us the wet paper bag has a ripping threshold of 57 newtons. So if it has to support any more force than that, the bag's going to tear open. So what maximum amount of acceleration can the bag be lifted with in order not to rip? Let's draw a picture to represent this problem a little bit better. Okay, here's our grocery bag with a couple handles on it. We're going to lift it. Inside you got some canned goods and fruits and vegetables and a block of cheese and a head of lettuce, whatever else. All the mass of that stuff is equal to 5 kilograms. And the maximum force that the bag can provide to those objects is 57 newtons. Okay, here's where a really important type of diagram comes up. You're going to be making things known as FBDs, not just for the rest of this unit of study, but really the rest of your study of physics. The concept of force is really important as far as determining the motion of objects. Whenever multiple forces are at play, you want to represent the forces in terms of their direction and their relative size. So you brainstorm a little bit and think, what are all of the fundamental forces that are at play in a situation like this? Well, what we do is make a stunt double that represents the objects in question. So you don't have to draw the canned goods and the block of cheese and the head of lettuce and so on. You just say all of the groceries can be symbolized by a dot. Think of it like a stunt double. What are the forces that are acting on it? Well, they're all attracted to the center of the earth. In other words, there's the weight of all that material. There's the force of gravity, and that pulls downward. So we'll draw a vector, an arrow of a certain length to represent the magnitude and in a particular direction that corresponds with the known direction that force is applied. And we'll label this, we can call it mg because we know that's the way in which we can calculate the weight of an object. But then again, there's the upward force that's going to cause it to lift. And that's provided by the bag itself, right? So, sure, the groceries make contact with the bag, but by Newton's third law, that means the bag makes contact with the groceries. And we're not so much interested in the forces acting on the bag as we are the forces acting on the groceries. So there's this upward force. Now, here's a concept to consider. If you want to lift the groceries upward with a constant speed, then the length of this vector and the length of the downward vector would be one and the same. If the upward force and the downward force are the same in magnitude, that would imply the net force is equal to 0. Whenever a net force is 0, the acceleration is 0. In that case, we say the object is in a state of equilibrium, and therefore the velocity would have to be constant. So once you get the grocery bag moving, a free body diagram, in other words, a vector diagram that shows the forces, would indicate that the upward force and the pull of gravity are equal. Okay, but I'm going to erase all that because that's not the case here. We're told in this problem to figure out for the maximum acceleration that you can provide. So if you're going to accelerate the groceries upwards as you lift, then the upward force has to be slightly larger than the downward force, so that the net force is not equal to 0, and we can determine the acceleration. So you can see pretty clearly in this case, when one force points up and another one points down, the net force between them would be nothing more than the force in the upward direction minus the force in the downward direction. And then Newton's second law tells us that the acceleration is equal to the net force divided by mass. Or in other words, the acceleration is equal to the lifting force minus the weight divided by the mass. So we're trying to figure out what that maximum acceleration can be. So if I want the max acceleration, that comes from substituting the maximum amount of force. And because we know the bag will break if the force exceeds 57 newtons, we have a numerical value. So in step 3 of our solution, it's just a matter of plugging in the given quantities. If we take 57 newtons minus 5 kilograms times 9.8 meters per second squared divided by 5 kilograms. Now note that a kilogram times a meter per second squared gives a newton. So this tells us the acceleration is 57 newtons minus 49 newtons, all divided by 5 kilograms. This is 8 newtons divided by 5 kilograms, which gives us an acceleration of 1.6 newtons per kilogram, but a newton per kilogram is the same as a meter per second squared. So there you have it. That's the greatest upward acceleration that you could provide without the bag ripping. One thing to note is you may have been surprised that I plugged in positive 9.8 for G. And some of you might be thinking, wait a minute, since it pulls down, shouldn't it be labeled as negative? Well, I've really already treated it as negative in a way by drawing the vector in the downward direction. And the fact that I subtracted that force from the applied force already took care of that. So if I had made it subtraction and also plugged in a negative value of G, right, the two negatives would have made for positive. So once you draw a free body diagram that shows the nature of the direction of the forces, then from that point on, all you're interested in is the magnitudes of these forces. Okay. Is mass a force? No. Is weight a force? Yes. Keep that in mind, so from now on, whenever you encounter a problem that describes an object of known mass, you can include in your free body diagram a vector that represents the weight of that object.